So here we have a partial differential equation of the form ut plus some function of x times ux equal to 0. And I want to talk about how to solve such a question by using a method called method of characteristics, also known as flow lines. Now, I'll just show you a nice example to solve, but before I solve a slightly harder one, let me try to work out the easiest case, where the easiest case will be when ax is just 1. So think of this easiest case where ax is 1, so you just have ux here. And let's assume that it has an initial condition. Here, u is a function of both x and t, and specifically at time t equal to 0, let's say it's given some initial condition as f of x. Now, this can also be solved by using the method of characteristics, but for this, it's easy enough that you can just check that the following is the solution. So just say that uxt is f of x minus t. If you have that, then let's see what happens if you plug this in here. So when you take fx minus t, differentiate by t, then this is an inside function. X is considered as a constant because this is a partial derivative. And so you're really trying to differentiate a function where it's a composition. This is the outside function, this is the inside function. So by using the chain rule, you differentiate the outside, and then you pull the inside out and you differentiate. Well, x differentiates to 0, negative t, because we're differentiating by t, it gives you negative 1. On the other hand, if you differentiate fx minus t with respect to x, then again, it's a function composition. So we use the chain rule. Outside gets differentiated. You pull the inside out and differentiate, but this time you're differentiating by x. T is considered as a constant, so you get a 1. And because when you plug this into both of them, you're basically adding these, you see right away that this has a negative 1, that has a positive 1. These are the same, so it's going to satisfy this differential equation. Now that solution immediately tells you why this type of differential equation is called the transport equation, because you can see that as time moves along, so let's say the initial condition is something like a bump function. Let's say some kind of a bump function, and if you draw the graph at time t equals to 1, what happened to this graph is that x minus 1 makes the graph move 1 step to the right. So after time t equals to 1, this will be time t equals to 0, time t equals to 1, it's going to shift over here. And then it's going to keep going right, so you see that this differential equation will just take the initial condition and keep moving right. If this is minus instead, and then it will keep moving left. And if you have bigger numbers, it's going to move faster. This next example will be certainly harder, and therefore we will need to use the method of characteristics. And once you solve this, you'll see how some other cases can be solved by using the same method, right? So the example I want to solve is when you have ut plus x times u x equals to 0. And let's assume that there's an initial condition ux0 equals to f of x. Now, since we're working with a plane where you have u is a function of x and t, instead of x and y, let's use x and t. If you have a two-variable function, you have something called the gradient. What's a gradient? Well, you simply differentiate the function by each variable. So you have a partial derivative with respect to x and partial with respect to t. You just write it as a vector. That's it. That's the gradient. Now, once you do that, you realize that this left side is exactly the same as if you were to take the inner product between x1 dotted with ux ut. Right? Because x times ux gives you that, 1 times ut gives you that, and dot product is a component-wise multiplication, and then you add. And this is basically saying that you have some kind of a vector and you're doing a dot product with a gradient of a function. And you may have seen something similar like this. Unfortunately, a lot of you forget the multivariable calculus after you learn it. So let's try to review what you did in multivariable calculus. In multivariable calculus, there was this concept of a directional derivative. So suppose you have a function u of 2 variables, x and t, and at this point, just forget about the differential equation. Just think about a function whose values are at each point. And to help understand what u looks like, just think about u as the elevation at each point, so it looks like a terrain map. Okay, so you have a mountain here, you might have some valley there, and some higher places, lower places. So that's how the function u looks. It's like a terrain map. It's a 3D thing. And you can think of something called the directional derivative, which is you take u and you differentiate. You want to find the rate of change of u going to a certain direction v hat. This hat means it's a unit vector. So let's say you have this point A comma B, and you're going, this is the unit vector v direction. Then this means the following. If you evaluate this directional derivative at A comma B, it means that you want to look at this terrain map, and as you go along this line, you want to see the slope of this function u. That's what directional derivative is. And in addition to that, in calculus 3, you learned the following fact, that you can calculate this using the multivariable chain rule, but the quickest, easiest way to calculate this is you take the gradient of u and do the dot product with v hat. And this looks very similar to this, right? So in other words, think of it like this. Think of it like you have this equal to 0. That's this differential equation. But then you divide this by the size of this vector and multiply it back. So it's the same thing. Or we can just divide this both sides. So since this other part is 0, you can just say this is 0. But that's a unit vector dotted with the gradient. So it's exactly the directional derivative. And this means that this transport equation is basically saying that at each point there's a direction where u stays constant. And it's really helpful if you can draw what that shape looks like. So let's try that. Think about, here's x, here's t. And think about when x is 0. When x is 0, you have 0, 1, which is a vector just pointing upwards, right? So when x is 0, it's the direction that's going straight up, where the value of the u doesn't change. What about when x is 1? Well, when x is 1 is 1, 1, and you divide by square root of 2, so it's 1, 1 is this, so it's some unit vector going that way, right? What about at 2? At 2, it's 2, 1, which is slanted further that way, right? And if you have negative 1, it's the vector going that way. And if you have negative 2, its slope is further that way, right? And then because this vector doesn't change as you change t, and t is always 1, that means along the vertical lines, the vector direction doesn't change. So it's going that way, it's always this direction. Over this line, it's always that direction. This line would be always that direction. It would be always this. And then if you imagine that you have a curve that's always tangential to these slope fields, then you see that the function u would not change over these lines. So look, if you have a line passing through here, it'd be like something like this, right? And line passing through here would be something more like that. This will be just straight up. This will be like this, like that. So you can see that that there's it gives you a nice idea of what's going on. That u is a function where at time t equal to 0, it's given by this initial condition. But the values of these, they tend to spread out, filling the whole space. So you can kind of draw what the solution graph will look like. So that already gives you a good idea of what the solution looks like. But I still want to show you how to actually solve this. So let's try to solve this by using this idea. Well, the idea is to just follow one of the characteristic curve or flow lines. And if it follows the flow lines, you can think of this as x as a function of t. So each point here will be t comma x, xt comma t. Hopefully that's not going to confuse you. See, usually we say y is a function of t, but here I'm kind of changing stuff. And the reason for that is because of this 1 in front of t. You'll see why. Okay? So if I assume that xt is a parametrization of one of these characteristic lines, characteristic curves or flow lines, then you can say the following. You have u evaluated at that point, xt comma t, would be a constant. Which means if you do a total derivative of u xt t, it'll be 0. Okay. Now, how do you do a derivative like this when t appears in more than one place? Well, you learned how to do this in Calculus 3 also. It's called the multivariable chain rule. And the way you think about this is you have to draw the dependence diagram. U depends on t and also x, right? But x is also a function of t. That's the dependence diagram. By the way, you can, once you see this, you can think of more general situation where this is also a function of t or something. And in that case, you may have to involve a third variable where, I mean, you can have this side as a function of x, as a function of t, and then I guess there are some conditions. I haven't thought about it, but yeah. But it will just give you some different kind of dependence diagram where you have x and y, and then they both depend on t, or you have t and x, and they both depend on some other variable s, something like that. Okay. All right. So back to this example. What we do is we now write down the chain rule. So the question is, how does u change when you change the value of t? If you take t and change it ever so slightly, then u is going to respond, right? So I want to see what's the rate of change of u under the change of t. Well, t affects u in two different ways. One is it affects it directly, not going through x. So we say one side is you differentiate u by t. That's it. But there's another way that change of t affects u, which is that if you change t, it's going to change x, right? So there's this rate of change of x with respect to t, but then that change in x is going to affect u as well. So you calculate that, and multiplying these two gives you the rate of change that t brings to u as it goes through x. And the multivariable chain rule, it's like magic. It just says that just consider all the ways that this variable affects this, and just add them up, and that gives you the total rate of change of u under t. And you're saying that this is equal to 0. Now, look at this, compare it with this. Aren't these almost the same? See, this is u differentiated by t. This is also u differentiated by t. This is u differentiated by x. And, oh, this is different. You have derivative of x with respect to t, and this is just x. Okay. So we see that the above equation will be exactly like this one if we had x prime. This is x prime, right? X is a function of t. So this, I wrote it as like partial, but it's really dx dt because x is not multivariable function. It's just the regular derivative. So x prime is equal to x. Oh, that's a simple differential equation. You probably learned how to do this in the very first class of ODE or the first week of ODE. So I'm going to skip how you solve this. A quick check is that if you take e to the t and differentiate, it gives you e to the t, right? So the generic solution, if you did this, you're going to see that the generic solution is any constant multiple of e to the t. That's the general solution of this. Okay? Now, moreover, if you plug in t equal to 0, you also see that x, when you plug in 0 for t, you get c times e to 0, which is equal to just c times 1. That's just c. So that what we call as c could also be written as x equals to x of 0 e to the t. Okay? Huh. All right, so this almost solves the question because this says that if you know x0, the point x position when t is 0, then this is the curve that follows. And it just makes sense, right? See, if you drew the graph y equals to e to the t, it's this graph, y or x equals to e to the t. But then since I have x and t switched, you flip this, it's exactly that graph, okay? Okay, so now how does this help us? So here we identify the characteristic line, and now what we do is we kind of rewrite this initial condition. So let's see. If I plug in 0 into t, we get u of x0, 0, and u of x0 is equal to f of x0, right? So all I'm doing is I'm just taking this and plugging in 0 both sides. By the way, this c and that c is different. Hopefully you're not confused. Okay, so if this is set to be 0, then that's like x0 comma 0, so that's exactly like having x0 here and x0 there. That's all I'm writing down. Okay? But then, because our x of t, this thing here, makes everything constant, if you follow the flow lines, or xt is x0 times e to the t of u, these two didn't change because it stays constant, so this doesn't change. And now what? You have this equals to that, right? Okay, we're almost there because, I treated this like a number, but see, this could be any number, right? So think of this like as a variable. So if I want, in general, what ux of t is, you just have to identify where this x came from. So this x flowed along this line. It must have started at some x0, comma 0, and it's it must have started at this value. So what you do is to set these two equal and say, oh, x is x0 times e to the t. Divide both sides by e to the t. Well, dividing by e to the t is the same as multiplying by e to the negative t, so you get x0 equals to x times e to the negative t. Okay, so since I know that this is same, so uxt in general is same as this one, is equal to this one, which is equal to this one, but x0 is x times e to the negative t. So now we have the final answer, which is that uxt is equal to the initial condition f evaluated at x times e to the negative t. Okay, so that's the solution. Let's check. If you plug in 0, what do you get? You get ux0 equals to f of x, which recovers this, right? And then if you took the derivative with respect to t, so ut, if you differentiate with respect to t, then by the chain rule, this is f prime times x times e to the negative t. And then this has to come outside by the chain rule, and differentiating this by t gives you negative x e to the negative t as a multiplication. On the other side, ux, on the other hand, ux, if you differentiate by x, that's f prime of x times e to the negative t, and you pull this outside and differentiate by x, you just get e to the negative t. But then look at this, you multiply it by x both sides and add up, you'll see that it's 0, right? So indeed you see that this will satisfy this left side. Okay. Now let's just go back to this earlier example and see how method of the characteristic lines makes this solution a lot easier to understand what's going on. So this one is like 1, 1 dotted with the gradient of u equals to 0, right? So in that case, the slope fields that you can draw will be always this way. So it's always this way. It's a constant. Therefore, the flow lines will be that way. So that's why everything should be moving right. So that's it. That's how you solve a 1D transport equation.